Hello again. In this video, we are going to discuss what the autoencoder is. Autoencoder is one of the most simple, straightforward generative model, and it can be used directly as a baseline, or it can be used as a building block for a more complicated architecture. So before we dig into the concept of the autoencoder, let me introduce one of my favorite way to learn a new concept or a things. That is learning from Wikipedia. There are many different sources that you can use to learn a new concept. Like you can use a lecture note, a book, a video tutorial, or even a blog post to learn a new things. Wikipedia is one of the source that you use to learn a new concept. So for me, I think it is more suitable for the case that a topic is very well known and mature. Then it perhaps using Wikipedia perhaps is a one way that you can start with. So what's the benefit of using Wikipedia as your start point? So first thing, if this is the first step that you learn this concept, chances are after a while you probably forget what it is, but you can always go back and check Wikipedia and refresh your memory. If you were using a book and you could not find the book itself, and you remember, okay, I remember I have read some sentence about this concept at somewhere, but just cannot find the book. Or you read something contradict to your memory, then you have some trouble because you still remember that you read something totally different, but just couldn't find it. However, if the Wikipedia is your original source, then you can always go back to Wikipedia. And if you find out that the sentence on the page is kind of contradict to your memory, then you can pretty sure you didn't remember it correctly because it is already there. You are sure you read it from Wikipedia. And Wikipedia has an edit history, so you can read the discussion and the history, and you can almost 100% sure you didn't recall it correctly. Moreover, if the article about this concept is well written, it will provide many references. So you can start from the Wikipedia page and go to references to dig more into the history and the more variation of this concept. So that's the major benefits of using Wikipedia as your learning material. Besides, if a concept is so popular and so common, like autoencoder itself, chances are the pages are well written and well organized. It almost already provides the information you most needed or wanted, and in a more concise way. You don't need to read a book like several pages or several chapters before you get into a point. Or like watching videos and never get to the point. So it is a fast, well-organized way. However, if you find out that you don't really understand what is written on the Wikipedia page, then that might indicate that your background knowledge is not enough. In this case, Wikipedia is not a good source for learning things. You need to go to a basic. And because Wikipedia provides some references, so in many situations, the suggestion or recommendation of the readings are good ones and popular ones. So you can go to Wikipedia and check its reference and read the book itself or a video or any the reference source itself to learn more things. There are also some cons about using Wikipedia as a source. One thing is it is a bit boring because every concept has a Wikipedia. It's like a dictionary. You cannot really learn all the language from a dictionary because if you encounter different concepts in different situations, it will become part of your life, your history. So remember, everything is different. Everything is unique to you. However, if you learn things from the Wikipedia, everything is simply from Wikipedia. There's no difference, no special about any concept. So it can be a little bit boring. And people turns to, a lot of people think Wikipedia is unprofessional. It's not rigor. It's kind of because it added a lot. So in that sense, it is not that reliable because it can be added by anybody. However, if you check the history, edit history carefully, and when you have suspicion and check the reference, do not believe it unconditionally, then it would be, I think it would be fine. Okay, enough for the method. Let's go straight to the concept itself. So I'm using this method to learn autoencoder because autoencoder is a well-known and a very popular, a very common concept. So it is one of the good example for learning things from Wikipedia. And after this class, and maybe a few months later or a few years later, you find out that you forget about what autoencoder is. You can always go back to the Wikipedia and find out the material. So most of the material in the slides are taken from Wikipedia. So you will find everything familiar. So this is the link to the autoencoder entry in the Wikipedia. Also, you can directly link from it. I'm not only using this entry. I'm also in the description in the following slides. I'm also going to introduce a little bit about PCA, Principal Component Analysis. I'm also using the stub that appears in that page. So what is autoencoder? First, if you read into the Wikipedia page of autoencoder, on the very first, not the very first, but near the first upper part of the top part of the article, you'll find the definition. And the definition goes like this one. Two sets, the space of decoded message X, the space of encoded message Z. Almost always, both X and Z are Euclidean spaces. That is, X is equal to Rm, and Z is equal to Rn for some M and N. Two parameterized families of functions. The encoder family are EV from X to Z, parameterized by V, and the decoder family d theta, Z to X parameterized by Z theta. Okay, so when we read about this one, this is might be a little bit confusing or difficult to understand if you are not familiar with the symbols and mathematical language and or symbols. But for most of the part, in the first paragraph, it's almost like a regular setting that is just a typical setting. So the first part is pretty much saying that X is a vector. X is just a vector of M component. There are some exceptions and non-typical case, but in general, you can first just consider X is a vector and Z is a vector. And we have two functions from X to Z and from Z to X. Both are some vector space. Still, you might feel this still a little bit confusing because it kind of define nothing at all. So this is what I said. You need some background and some technique in order to really use the Wikipedia as your source. So try to do this a few times, and if you feel comfortable for reading these things in, the definition and the styles in Wikipedia, then Wikipedia will become one of your very powerful tools. So, but I will break this down into the following image. This image might be a little bit easier to explain what is going on here. So basically, X is just a vector, just a simple vector of some length from, and like the space X in the definition. And there's a function which may be modeled by a neural network or some simple, maybe even easier, like a linear function. But typically, it should be a proper neural network or maybe a deep one, maybe a simple one, maybe a deeper one. But in this case, we just call it a function. So we are mapping this function takes X as an input. So X has a fixed length, some certain length is a vector of certain length, and the length is equal to the input dimension of this neural network, and the output of this neural network is a vector H, which we call the latent or code, and the function here itself we call it encoder. This is what we call the encoder. And for the other one, we call it decoder. It works reversely from H to X prime, from H to X prime. It takes almost like the encoder, except the dimension, the output dimension, the input dimension of this decoder is the same as the output dimension of the encoder, and the output dimension of the decoder is the same as the dimension of input dimension of the encoder. That's all. That is all this definition says. We have an encoder and a decoder. The decoder, the domain, the range of the encoder is, the domain of the encoder is the range of the encoder, and the range of the encoder is the domain of the decoder. So which they just exchange from the input space and output space. That's it. That's it. It doesn't say much. Yes, it doesn't. You are correct. It doesn't say much, but it is very common in the abstraction of things. Usually, people want to generalize things and to make things more abstract. Very often, it is too abstract, so that it become almost, almost lose a lot of typical characteristic of this autoencoder, like in this case autoencoder that we usually use. It only keep the very, very fundamental and the basic part. That is, it has an encoder and a decoder, and the encoder and the decoder has the input space and the output space are, the output of the output space of the encoder is the input space of the decoder, and the output space of the decoder and is the input space of the encoder. That's it. So the other properties that we usually assume to belong to the autoencoder usually has further definition, like a further property or further thing. It only keeps the basic, very basic property. Sometimes the definition depends on context. So usually, always look what the book or the article try to say about this terminology. Okay, so this one definition is from the Wikipedia, but in general, we not only the autoencoder is defined in this way. We are mostly interested in some specific particular certain autoencoders. If we define autoencoder in this way, then we are mostly interested in the autoencoders that has certain property. So what is the certain property? The certain property is like this one. So suppose we have an autoencoder. So you can see that this one is simply an autoencoder. From x to f, no matter what space it is a function from x to f. And then this is encoder, this is decoder. Also decoder here is from f to x. So this is an autoencoder if we consider the pair of encoder and decoder. Then we almost wish that if the phi and the psi, these two functions, the encoder and the decoder, are, in mathematical saying, we wish this one to be the left inverse function of phi, the psi to be the left inverse function of phi, which means if we map something to phi and then get the output and send it to psi here and get a new output. So this one is from the space x here and to the space f and then go back to the space x. So it go back to the same space. Not only it go back to say, we mostly wish it to be very close, or if it would be the same thing, that would be perfect. But if it is not possible, then we wish it to be as close as possible to the original input. So basically, the autoencoders that we are interested in are the autoencoders that works like the encoder and the decoder works like a inverse function, or the decoder works like a decoder function of the encoder. So this setting has been used a lot, not only in machine learning, we like compression. So we usually compress, I will have a video and we do some H264, H264, H265, like the MPEG or other video compression algorithm. We usually compress these videos into some format, video format. And this format can be, when you put the files into a player, it can play back and decompress into a video that we can actually watch. Although there usually will have some loss because the decompressed videos is not exactly the same as the input. There always be some loss, depends on the compression ratio you use. However, we are expected that the output, the decompressed, the playback video is very, very close to the original one. So that can be considered a kind of autoencoder, a very specific, a very particular way of type of autoencoder. So other things like, in fact, all compression can be considered as a autoencoder because it has an encoder and a decoder. The auto means to self. So autoencoder means we from X and then go back to X. Okay, so that's, if you want to understand is the definition, then that is the definition. Not more, not less. This is just a definition. A simple example is that if we consider the encoder and the decoder all to be a very simple network. For example, like this one is just a wx plus b. This one is encoder itself, and this one is sigmoid. So it is the logistic regression. This is simply the kind of look like a logistic regression things because you have a linear. You guys say you can say that affine transformation and sigmoid. And after you get the output, this one is going to be the latent, and you have a sort of inverse affine transformation, and of course you have a sigmoid right here, nonlinear part right here, and you go back to the. So this one is an encoder, and the outside one is a decoder, and we hopefully we get them the x after this encoder and decoder transformation, and then get a new one called x prime. Hopefully x and x prime are close, are very close. Also, this one is a simple form of maybe the original autoencoder. I'm not entirely sure. We should refer the autoencoder to this one, but this one is one of the typical autoencoder that we will consider about. It's very simple one, almost linear, just a linear with a nonlinear activation function. So this one, because you can, this one is a loss. So by using this as a loss, with any kind of data, you can train your autoencoder without any manual labeling, because every data can be used as a training dataset of the autoencoder. You don't need to label anything. So here's some history about the autoencoder. So back to the it is originally considered as a generalization, a nonlinear generalization of a PCA, principal components analysis, which we are going to talk in detail a little bit later. It originally has different names, like auto associator or diagonal networks. I have not ever encountered the usage of this terminology, but apparently some people, I mean, at least at some field or some periods of time, it is not the only name of this kind of setting. However, right now I think autoencoder is much more popular than the other names. Its first application can be dated to so as early as 1990s. So because PCA is often used as a dimensional reduction or feature selection, feature learning method or algorithm, so it's not surprise this kind of things can be considered as more advanced or generalized algorithm of PCA. So it can be used as a dimensional reduction and feature learning. But as we can see that it can be also used as generative models. So how do we use it as a generative models? There are many ways to do that, but simply we can only use the decoder part. We can simply use a decoder part. So because so for example, if this is kind of I mean your X space is images like MNIST, and your F is some typically very short length. That means like a latent of length of like 16 or let's say just 10, just like our MNIST classification. So if this is a very short or small space, then we may assume that there are very big chance that when you pick any element in this space, or there are good chance that it will generate back to some valid images. So that is one issue that if when we use this as generative models, there's always issue is that we don't actually know. We know what f is, but not every element in f is valid, because we know that x, we map this encoder maps x into f. So there's only a subset of f can generate, even if our autoencoder is very trained very successfully. We assume that, but even if it is successful, there can be, there's generally only a subset of f can generate, can be decoded into a valid image. So we don't know what kind of subset that is. So there are some ways to determine the good subset of this, or in variational autoencoder, we force a good subset of f, or force x to maps into a predefined or good subset of f, actually a predefined distribution in f. So we can easily use that predefined distribution to generate new samples. So it is an issue, but in principle, or after it is possible to use autoencoder as a generative model. That is for sure. Okay, so it can be also used for generative models. And at the very beginning of the deep learning, when I say deep learning, I mean people start to stack the models to have more depth. At I think before 2000, year 2000, in the 90s, it's very difficult to train more than 2 hidden layers, because we already know that a neural network with 1 hidden layer can be universal approximate to any function. So although that is just a theoretical theory, you need a very, very wide hidden layer. But it is very difficult back then to train a network with very deep to train a very deep neural network. So in practice, neural networks usually just has 1 or 2 hidden layers. But people explore to use to design neural networks with deeper deeper neural networks with more hidden layers. It is not easy, although it kind of like a non-issue, because we have a lot of new techniques, like Bayes normalization for one, and the skip connection and other things. So it's kind of become non-issues right now, but there has a lot of attempts. One attempt is to train some autoencoders and stack these autoencoders together to become like you pre-train the layer to have a more reasonable weight of each layer. Then you stack them together and do a fine-tuning like that. So that has been used in the early years of deep learning. There are a lot of different techniques like this one. Okay, so why would we even need an autoencoder? I know perhaps some of you have a question, because it kind of seems obvious or trivial to train such a model. If you really look at it, usually neural network is used to approximate a function, because we say that we already know that neural network is a universal approximator. So it's very common. We know that it used to learn some function. For example, in the MNIST case, we learn a function to recognize the handwritten digits. But it usually we are trying ask the neural network to learn something difficult that is very difficult to write an algorithm. Otherwise, we just simply write the algorithm and solve the and just finish your work, solve the problem, and we are done. So usually we are trying to ask the neural network to learn some function that is not easy to write the algorithm. However, this function, this function fx is equal to x, this function, it is not simple. I mean, it is trivial. It is just simple trivial. We don't even need any algorithm. We just copy x and output x, then we are done. So why do we even need to ask a neural network to learn these so trivial things? So, for example, if we have a linear model, then the linear model, we just ask the matrix to be identity matrix. That is, it has all 0 except for a diagonal. Diagonal is all 1. So this identity map maps everything to itself. This is the simplest matrix or linear transformation. So why do we even need to learn this function at all? Of course, you're right that we don't need manual labeling. But in exchange, we learn something so trivial because it doesn't require people to label it. So the problem cannot be too difficult. It is because it is so easy. So we don't need people to manually label it. Okay, so why do we even need to learn this function at all? The reason is it is still difficult. Although metric is, I mean, the simplest metric like identity metric is a perfect autoencoder. You can put it as an encoder and a decoder. The thing is, we usually require this function f to be a weaker, smaller space than this one. So like compression, video compression. Of course, you can you can do a lossless compression by simply copy the file to itself and copy it again. So the first copy served as an encoder and the second copy served as a decoder. It would be a perfect autoencoder. However, our setting is usually more restricted. We usually require this f to be worse or a smaller space. So it is kind of like this one. Consider you have a hard disk or storage that is 1 TB, 1 terabytes. You have a lot of files. If f is strong as x, it is still 1 TB, 1 terabytes. Then this is just like we say, it is non-issue because we can copy to here and copy back to itself. So we back up the file, and when everything finished, we copy back it to the original storage. There's no issue. However, for the setting of autoencoder, it is more like this is 1 terabyte, and this is let me make it more dramatic. It is 1 gigabyte. Okay, so this only has 0.1% storage space of this one. So the challenge of autoencoder is we want to back up 1 terabyte data into a storage that only has 1 gigabyte, and then we wish it to be restored to the original one, and the restore should be as close as the original as possible. So it's very difficult. In some settings, it is impossible because this is what information theory originated from. that we know that it is impossible because they have different, they can contain different information capacity. So this one is huge capacity. This one is very little compared to X. So in principle, in theory, you cannot have a one-to-one copy back, backup, and restore it into the original, uh, storage. The only catch and the possibility is that just like the videos, we know that this is a very sparse. The videos, if we store it pixel by pixel, consider we store it pixel, it will take a lot of space. And if we only consider the valid image, I mean the videos, it is only very, very small percentage in small portion in the whole space, whole possibility files that can be stored in that kind of storage, say that is 1 terabyte. If we save the videos pixel by pixel, frame by frame, each pixel and the frame, each frame is uncompressed. It's not compressed at all. Then we assume that the space that we are interested in is very sparse. There are only very, very few possible files that are interesting to us. In other words, if we randomly generate a file in this 1 terabyte storage, it is we almost have zero chance to get a valid video images and pixel by pixel and frame by frame. So that is one way to show that the space that we are interested in is very sparse, because if you really randomly generated something, it is almost sure, almost impossible to generate something interesting. So the only problem is we don't know, although we know the space is far less than 1 terabyte, we don't know which space it is. So the autoencoder, if it can work successfully, then we might be able to use only 1 gigabyte to store, if we only consider the video, not those random noise. We don't need to perfectly restore, back up and restore those random noise. We only need to back up and restore video files. If we only consider video files, then it is possible. I mean, at least it has some chance that we only use 1 gigabyte to restore, I mean to save, to convert these MV video files to 1 GB into is 1 GB, and then we restore it back to the 1 terabyte storage. So that's the idea, and you can see that it is difficult. It is difficult. So although this function in principle is not difficult, but if we have some restrictions, it will make it difficult. So it is not too easy. But in some cases, it might be too easy, still too easy, even if we restrict it to a small space, a more restrict latent space. It can still be too easy. In that case, we may add some more restriction, which we'll talk about later. But you can think that is not easy to control this kind of function, because we have some restriction on the function space. We cannot simply use any function. So when you consider autoencoder, the bottleneck, that is the latent space, is really important. If you have a really big latent space, that cannot even call it a bottleneck, because it is even larger than the input space. Then the autoencoder, there's almost no purpose to, I mean, you don't I don't know why you need to train this autoencoder for the exactly the same reason, because it is too easy. There's no meaning to training a identity function unless you give some restriction. Okay, so let's talk about PCA. So as we mentioned before, we can consider that let me see how long we have going to take. Okay. Autoencoder can be considered as a generalization of PCA. That it stands for Principal Component Analysis. So what is PCA? What is a PCA? Basically, as we can see before, if you already know, have a concept of autoencoder, then it is very easy to know what PCA is. We're kind of working backward in the sense of history, but we already got the definition of autoencoder. Okay, and so if since we already know what the autoencoder is, and so PCA is simply is roughly an autoencoder that the encoder and the decoder are both linear. When we say linear, it is really linear. There's no bias. There's no bias at all. You can add a bias, so but the bias is always the mean of the data. So basically, it is not affine. It's just pretty much assume that the data has mean 0. So the encoder and decoder is exactly linear, or not even affine. It's just linear, and there's no nonlinearity like the sigmoid or any activation function. Not at all. It's just linear. As we mentioned before, if you have a simple linear like identity matrix, then of course you can do things like perfect copy X input, copy the output as the input. I mean, it is identity function. So the same thing is that when we consider PCA, if you consider as an autoencoder or like this way, it is typically that the latent space is a little bit smaller than the input space. So it's kind of like if you have heard like LoRa, or like LoRa in fine tuning large language model or division model that's usually used is called low rank adaptation. In LoRa, it replaced the full linear metric part to a metric that has low rank. And then the low rank metric works kind of like PCA. So because it has a bottleneck, it is a multiplication product of two metrics, but these two metrics are not square, so it has a bottleneck, like an autoencoder. But it doesn't necessary to have one, because PCA is not only just a linear autoencoder with a linear encoder and a linear decoder. It need to have certain properties. So roughly speaking, the restriction is the components are ordered by their importance. So we kind of choosing the most important component, and the second one is the second most important. The third one is the third most important one. So what does it mean by importance? So consider this kind of a distribution. We generally consider the longer one to be the important one, and the shorter one is the less important one. And you can see that this one and this one are orthogonal. So it is you can prove that every component of PCA are orthogonal. Okay, in precisely speaking, what is the most important component of that distribution? So basically, if we try to find out the most important one, we simply, because this is a two-dimensional space, we simply consider every direction. In this one, we can work like counterclockwise. So because it is just, because it's two-dimensional, so we can work through all the directions by a rotation. If it is three-dimensional or higher dimension, you have to try all kind of different directions. But after we try all the different kind of directions, for each directions, we project all this, because we imagine that we want to reduce our space into one dimension. If we only need, if we can only choose one dimension, how do we choose the most important one? So we run through all of them and measure the importance of each direction. So the measurement of importance is that we project every data point to this direction. So like a shadow, it just kind of like a shadow. Projection is like a shadow, but you just put the orthogonal direction on it. So we, for each data point, we we ignore, we discard all dimensions except for this dimension. So it will reduce a lot of things, will discard a lot of things, and only everything is projected on this dimension. So then we have a lens, because when we project it onto this dimension, the lens will shrink a little bit, because it will reduce other component, other direction, the component of other direction. It only keep only one direction. But for every direction, it has to sacrifice something. But for which direction, it sacrifices the minimum. Then that direction is what we are looking for. So in other words, we'll consider, I can see that the W is a direction. So we do the dot product or projection. We just simply do the dot product, project it onto the that dimension, and compute the total length remains on that direction. So if we simply shrink or scratch everything into this dimension, we must sacrifice something. So we choose a direction that will sacrifice less. So that, in other words, we keep the most, because we sacrifice the minima. So they are the remaining are the maxima. So we choose a direction that we still get the most thing, even if we do the projection to that direction. So that is this formula S. So we find the first one, the most important one. After that, we remove the first dimension, the most, and we do the same things again. Then we can find the most important one when we remove the first one. Of course, the other one is working in the orthogonal space of this space, so it must be orthogonal to the first one. And the remaining has to be less than the first one, because the next one is the champion of all direction. The second one is only a champion if we remove the first one. Okay, so after we got the second most important one, then we got a third and the fourth and the fifth and all of them, and we can order them by the importance. So we got, this is the algorithm of PCA. which we call the principal component decomposition. And when we consider compression or dimensional reduction, then obviously we should keep the important one and discard the less important one. Okay, so that's pretty straightforward, and there are algorithms for doing this one. The typical algorithm is using the SVD. So standard, we can doing the SVD. There are a lot of algorithms to do the SVD and can do it more very stable. So if we decompose the metric into its single value decomposition, like this one, then we can write the T. T is the you can consider it as the PCA, PC principal component decomposition. Then the T is XW because it is W, and it can be write as this one. And this W is exactly this W. So that's why we can write this one. So SVD is closely connected to the closely related to the principal component analysis, and we can compute it we can compute this really easy and stable. So that's why people, but it's still, if you have like a lot of data, PCA, because you need a lot of data to store the matrix itself, so the matrix will be huge. So usually if you only have like 10,000 or 100,000 or maybe even 1 million data, then it is okay to use PCA algorithm directly. But if you have more than 1 million entry data, then it would be kind of difficult to use that. So there are some approximation or distributed PCA method to compute it. But if you don't have that much, you only have like say 100,000 data, then because chances are you can use like a scikit-learn to compute the PCA. So if we consider the PCA and the linear autoencoder, although PCA, like we say, it is a special kind of linear autoencoder, it has additional properties. But if you train the autoencoder properly, then it will look very, its behavior would be very close to PCA, because neural net has to use the data space efficiently. So although no guarantee, but in many situations, it will be very close to the result of PCA. So for example, in this example, it's just a rotation, because you cannot control a rotation itself. But after a rotation, the PCA result of PCA and the linear autoencoder are very similar, because after all, they are just a linear transformation into the same size of latent space. Okay, so what is the time of using, what's the proper time of using PCA or even autoencoder? So in my opinion, if you have some generative task for image generative or even some sample, you don't have off-the-shelf pre-trained models. You have to train it by yourself, and you're not you are not that familiar with like diffusion models training or generative adversarial training. Or if you find, even if you have some confidence, but you find that you have trouble to actually train it successfully, then you can probably try PCA or linear, not linear, the autoencoder first. Because if you are doing things correctly, it can be very difficult to go wrong with this simple method. There are a lot of ways to go wrong when you use a more advanced techniques like diffusion model or GAN. Of course, like GAN is very notoriously difficult to train. So there are many things you can go wrong. However, autoencoder is especially if you are using a simple autoencoder. Usually, the training is not a issue. You can usually train it easily, and the training is easy because it is simply like a supervised learning. Basically, it's just a supervised learning with the label is equal to the input. X is equal to Y. That's all. So you can use all your knowledge to fine tune. To tune your hyperparameters. For PCA, it is even simpler because PCA has an algorithm. You can just use SVD. You don't even need to train. So there is much less place to go wrong. So you can replace your generative model with a PCA or an autoencoder. Although, like we said, that the latent space is kind of unpredictable or not easy to control, but it is easy to train, and you can get your baseline easy, and it doesn't take much time. PCA, if you fit a PCA, it only take like 5 minutes or 10 minutes. Typically, only take 10 minutes at most. It doesn't cost you much, and you have a simple baseline. If your complicated model, like diffusion model or GAN model or even more fancy models that cannot even beat your PCA or autoencoder, then you know you must have something wrong, because easier model can already achieve some predictable results. Not necessary to be very good, but because if you are familiar with these models, you already know the capability of these models can do. So even before you actually do the training, before that 5 minutes or 10 minutes of fitting a PC model, you probably have a rough idea what you are going to get. So I suggest everybody, if you're doing something that can be used as an autoencoder or generative models, do it with linear model. PCA model, linear model, or autoencoder first. Okay, there are a lot of different creativity method to use these autoencoders. So for example, sometimes the learning f of x is equal to x is still too easy. So there are some chances that you are very difficult to narrow down the bottleneck, or you don't want to narrow down the bottleneck, or you can't. Then in this case, you can do something to along the same idea without narrowing your bottleneck or making a bottleneck or making your latent space to be a bottleneck. One way to do that is to add some noise. So that is, before you're feeding your X into F, you corrupt your image, like adding some noise and hoping F to reconstruct this X back. So in fact, the current diffusion models are pretty much simply just doing a denoising autoencoder. Essentially, every step of a diffusion model is simply doing a denoising autoencoder. It's that way. Kind of. Not the most straightforward. There are a lot of different variations, but it's sort of just a denoising autoencoder. And another popular way of adding noise is to mask the data, like remove part of the data and hoping the function to predict or like fill the missing data. So in this chance, in this case that the neural network or the function can learn some fundamental relations between all these components. Like we say that a generative model is more about the correlations between components, or like I would say the structure. So in this case, it kind of forcing the neural network to learning the relationship between different components, so that it, even if we uh, omit some component or mask out some component, it can inference back the component. So this method used in a lot of different situations, like the masked autoencoder, or in some language model training. So this idea used a lot, or very often. But the basic idea is, I mean, is just add some restriction without human or manual labeling. You have a lot of way to add some restriction or making it more challenge. And all of this kind of thing we can categorize into denoising autoencoder. So the denoising autoencoder basically usually has some assumptions that higher level representations are relatively stable and robust to the corruption of input. And if you want to perform denoising well, the model need to extract features and capture useful structure in the input distribution. This is kind of summarize what we just talked about. It has to, this is the structure, and this will make it more stable, make the output to be more stable. So the training of the denoise autoencoder looks like this one. It can be abstract into this one, but I mean what is a noise is can be there's a lot of possibility of adding the noise into it, but basically you corrupt the input into something usually has less information, because sometimes it is impossible to have a bottleneck as a latent. Your latent must be it's a very large space. However, you can restrict the information pass through by corrupt the data directly, so making the information does not contain every copy of decision into every layer of the process. So first, that forbid the information to pass through all the way to the back. So to force the neural network to learn something meaningful. Okay, so given the corrupt X into it, and you put the corrupt data into a neural network and try to reconstruct the original one. I'll try to reconstruct the original one. I'll recall that you don't reconstruct the corrupt one, you reconstruct the original one. So if your corruption is a mask, like removing some part of the data, it will generate the missing data. If it is noise, make it more unsure, then it will become denoise. Okay. So there are many applications for autoencoders. Some typical ones like dimensionality reduction, information retrieval, like because we have a latent, so we can use latent space to compare the similarity between several items. We use the encoder only and get latent and compare different things. And also anomaly detection and the image processing. There are many ways to do that. So I would like to focus more emphasis on the anomaly detection, because this is a lot of people do that, and hopefully to try to actually apply to some real work pipelines. So for example, this is some of our research on using diffusion model to do the anomaly detection. So basically, we are training the data on normal samples. So we let the autoencoder. This one is actually using diffusion, model, but the idea is same. So let's just call it autoencoder. So we are using the autoencoders to encode the image and reconstruct it back by learning from the training data contains only the normal images. So we are kind of hoping that the neural net can work better on work well on the training data set. That is the normal images, which is an image that doesn't contain some defect or anomalies. So when we apply to an image that has defect or anomalies, what we are hoping is that the autoencoder doesn't work that well. The reason we can kind of hoping this happens is because we know that in machine learning, a lot of it is very easy to overfitting or at least has some data drift, so that your model works very well on the training data, but doesn't work very well on data, on test data, or on data has different distributions. So we are hoping that although it works really good on normal data, but when it can encounter a different distribution, it works not as well as the training data. So if that is the case, then we can tell the difference between normal data and the test data because they perform differently. They perform well, which means the reconstruction is very close to the original one. However, it doesn't perform well on the out of distribution, like the testing data or data with anomalies. So the reconstruction will not be that good. Okay, so that is what we are aiming for. For this one, you can see that when we already train our diffusion model, and we all, of course, we already add some. Basically, what we are doing is we put some noise on images and trying to reconstruct the image back. So it works like a denoising autoencoder. So when the input image is like this one, it's like this one, then we add some noise into it and using the denoising autoencoder to denoise back. It will denoise back to something like this one. If you were working on autoencoder denoising, just simple autoencoder, usually it doesn't work that well. But we are using the sort of diffusion models. It's surprisingly it can even reconstruct the legs right here because you can see the anomaly here. It's missing legs. It's a missing leg. We kind of if expecting that this one can be some noise or like some garbage image right here, corrupt image right here when do the reconstruction. However, it went surprising well because it even reconstruct the legs. It actually looks quite convincing. So this one is one of perfect case. So actually diffusion model works very, very well. So in this case, if we compare the image and the reconstruction, we can see a lot of place are pretty much the same. But this one, at this place, their difference is huge. So we can actually, not only we have found that this reconstruction is different from the original one, we can actually pinpoint where the anomaly is right here. And from this reconstruction, we can even tell the user what is supposedly to be normal. So if it's going to be normal, it will should be look something like this one. This one is another case that is typical that the anomaly is not that easy to be found. It also it's very small. So, but you can see that at least from the heat map, you can see that there's something different right here. So it the supposed normal pattern of this thing should be more regular or more like a grid right here. So definitely you can see that this one is anomaly right here, and of course this one is anomaly. But it compared to the above one, this one is a little bit difficult to spot on these anomalies. However, you can see that at least, although it doesn't reconstruct perfectly into a normal case, it still have significant difference between this one, and it is normal enough compared to the original input image. At least for this one, I guess this one's perfect. This one has something a little bit irregular right here, a little bit, but much better than this one. So, but no matter what, we can easily spot the difference right at these 3 points. There might be some minor difference, but I cannot tell. So by using this method, we are able to use the autoencoder to detect the anomalies. Okay, so we also have some example code that we can use, and we have a homework. Okay, so I provide 3 different example code right here, but I recommend this one, the lightning, which if I have a code that I have to write it from scratch, I probably will choose PyTorch Lightning. But PyTorch Lightning is a lightweight layer above the PyTorch, so you can easily convert any PyTorch modules into a PyTorch Lightning modules. So if you have no preference, then you can choose this one as your beginning. Okay, so just like any PyTorch code, you need to have a data pipeline. So this one is a typical PyTorch data pipeline. However, we don't need to do much because in this case we are using CFAR10. Try to apply autoencoder on CFAR10. So it has already written, so you can use this kind of things to make a data pipeline. You have a training, dataset, validation, and testing. The only thing you need to be careful is the number of workers right here. And transform. Because a lot of things need to be considered is the transformation of an image. This is something people usually, very often people get it wrong because it is easy, but if you scale the image in a different way, you do the pre-process of the image in a different way, then you will get a very strange result. Also, be careful to what your transform is. Always aware of what the transformation you are doing. And another thing, you need to be careful is the number of workers. Usually, this is non-issue if you are using Linux. However, if you are using Windows, this might be a problem. Usually in Windows, I will just stick with number of workers equals to 0, because this is because the operating system is very different from Windows and Linux. The same thing applies to like FreeBSD or Mac OS, because this is more doing the multi-thread or parallel workers. This is more like operating system things, so they implement differently. Because Linux is more like a major operating system, a major platform for deep learning, so the support is much better than other platforms. So this works just fine, except for the case that you don't have enough memory. You may want to reduce it a little bit, but it usually just works just fine. However, on Windows, there are some ways to make it work, but it is difficult. Sometimes if it works, it will have some errors after running a while or have a undesired result. So for me, if I'm working on Windows, I'm always setting it to 0, and don't even bother to adjust things. But you probably should just work in Linux, or if you on Windows, you can use the Windows subsystem Linux too, to kind of mimic the behavior of Linux. Okay, so the encoder is simply a sequential model, very straightforward. So it is using a convolutional neural network all the way down here. You can see the stride. Well, the stride is 2, so the size of image will reduce to half, from 32 by 32 to 16 by 16. Here we also got another, stride is equal to 2, and we got this one thing. And because we got padding is also 1, so it will has a perfect half the size. And it all the way back down to 4 by 4, and flatten it, and we get 16, a 16, the size of 16, the latent of the size of 16. Okay, then the decoder is pretty much the same, but in the other way around. It uses a convolution transpose. The stride is always as like a 2 when the stride is 2. The convolution transpose will will double the image size. So it, from 4 by 4 to 8 by 8 to 16 by 16, and finally to the 32 by 32. So, and you also need a forward right here. So these two are simple Python module, PyTorch module. There's no lightning whatever involved with it. However, the benefit of using lightning is it provides a standard way to do the training and pre-processing or configure or saving the checkpoint. It is very similar to the regular PyTorch module, but right here it is exactly the same, except it has a save hyperparameters right here, so you can save hyperparameters into a log file. So that's one of the benefit, because it provides a standard way to log your training. And otherwise, it's the same as regular PyTorch module. So you have a encoder, decoder defined. The example input array is just used for visualization. It doesn't, if you don't want to visualize it, the reason you need to use this one is because the input is not defined yet. So you need to kind of provide some hint information to tell the model what the size of input is. Okay, the forward function is like what PyTorch is. It's pretty much very straightforward. You get the input and you feed it into the encoder and get a z latent. It even have the same notation, x and z, and your latent, you put your latent into the decoder and get your reconstruction right here, and you return it. The slightly different things right here is you define your training step. It is independent to the forward things. You can call the forward, but it's written in a different way. You have an option to make it totally independent to the forward path. So you write what you would like to do in the training step, and you can also write a log right here. So if you were using the TensorBoard callback, it provides a lot of different callback in Lightning. So if you are using TensorFlow or using other log backend, it will do the log for you if you were using its .log method. And you need another thing to configure the optimizer. There are some ways, I mean, at least in previous version, there are some other ways to do the configuration for the optimizer. But right now, the document is writing in this way, and I think it is okay. You just, it kind of, it's sort of unsatisfying if you wish to try different optimizer. However, in most cases, this is good enough. And it's just different way to writing things, to write things. So you put everything into this lightning module, and then you can train the models like a psyche model. You use a dot fit and feed in the model and the loader and the variation loader in it, and you are done. It will train for you automatically, and you're getting a very pretty progress bar. And if you give some options saying, okay, please show this at the end or after each steps, your progress bar will show you very well, pretty showing the loss on your progress bar. And if you are setting, you have already set the TensorBoard backend for logging, everything will be saved into TensorBoard. So this one is the same Jupyter Notebook result that save everything into a TensorBoard, and you can actually show the some pretty visualization right here. Okay, so about homework. So this is our first homework. The due date will be a lot later. Perhaps like so you will have at least, because it's just beginning of the semester, so I'm giving it a more extended time. So you will have 2 weeks to do so, or maybe even 3 weeks, depending on the situation, because I know that a lot of people still have some trouble to register the class. So maybe so let me just make it 3 weeks. So the due date is, you still got 3 weeks to do that, and you can still work on it a while. But the homework is that you are going to train some autoencoders using the dataset MNIST and the fashion MNIST. These two are pretty standard. I am pretty sure you know that what that is. Even if you don't, you can just simple search this kind of thing, or you can ask the TA if you really have trouble to finding out these two datasets. What I want you to do is to train this train autoencoder on these two datasets with different latent dimension. Start from 64 to 32 to 4. So by various in the latent dimension, you can see how well the reconstruction is compared to the original one, and depend on the latent dimension. So is it enough to have a dimension only have 4? If your latent dimension is only 4, does it even enough? Does it even contain enough information to reconstruct the image? So suppose it is enough for the digit. Is it enough for the fashion MNIST? Fashion MNIST contains the image of like the clothes, jacket, shoes, or pants, like that, those kind of things. So this work give you some feeling about what the latent is, and give you some basic skill set that to train a successfully train an autoencoder, and observe the difference between latents. So hopefully you will get an idea of, okay, when you see a data, you can kind of guessing the latent is required to reconstruct this kind of image, because actually nobody knows. Like we said, that we kind of assume our data is sparse on a manifold in a large space, but we don't know even know the dimension of that manifold. So this one is a skill that help you to kind of guess, imagine what the dimension might be. And also you need so after you train this kind of things, what you should show in the notebook is the mean square error and the L1 error on the training and the testing function. So this one is the measurement. For training the autoencoder itself, you may use any kind of loss function you wish, a combination of mean square error or L1, anything you wish. However, I want you to evaluate your result by using the mean square error and the L1 error, and to see that is there an overfitting between the training result and the testing result. Okay, so this one, and compare your, this one is related to the purpose that I wish you to see how, what is the dimension needed for the latent. So by this numerical result, you can see, okay, the dimension, 4 dimension seems too little. Dimension 4 seems too little, but 32 is enough. It doesn't help much if we add more dimension. So 32 might be the right thing. You can do this and see the numerical result and judge by yourself. Another way to judge the quality is by simply showing the images, because all this like arrow or metric, there are a lot of metric to do for the to measure the quality of image. That's called the image quality assessment method. A lot of nothing is so far, nothing is perfect. People still looking for just a lot of methods, but nothing, not a single one. There's no one single best method. So there's still useful. It's very useful to look for the image by your own eyes, so you can judge the result by your eyes. So I need you to show the result images. So you show the 14 reconstruction image for 16 reconstruction image for 16 random images from training dataset. You can put it in a 4x4 grid. For it, there are actually 6 settings, so you do this 6 times and do the following 6 times. You can use any framework like TensorFlow, PyTorch, Lightning, and please provide your works in a single Jupyter notebook and show this thing, submit to the E3. Okay, so that's all for today's autoencoder, and I hope you enjoy this tools, because it is really a wonderful tools that you can use in many situations. So see you next time.